Hello everyone, my name is Cheng-Yun Tsai from National Taiwan University. Today, I will be presenting our work integrating spatial proximity and visual feature similarity for crew group detection in construction sites. So first is our introductions. Unlike industries such as manufacturing or factories, where environments are relatively controlled and highly automated, the construction industry still heavily relies on labor as the main driver of productivity, which makes labor force analysis become a crucial role in construction site management. Traditionally, methods like work sampling and field rating were used to measure labor resource. However, recent advances in computer science and deep learning frameworks allows us to transition to automated systems for real-time monitoring, enhance accuracy, and increase efficiency. These shifts help eliminate human error and reduce manual observation efforts. On construction sites, most workers typically collaborate in small teams to carry out tasks. Understanding the productivity of these teams is crucial for improving overall efficiency. However, most of the existing research has primarily focused on analyzing individual workers, often overlooking the dynamics of team collaboration and group performance. Our study aims to fill this gap by exploring how we can apply these technologies to detect worker groups based on both their spatial and visual similarity. So the main objective of our study is to develop an automatic framework that can detect groups of workers on construction sites. We aim to achieve this by integrating spatial proximity and visual similarity using a graph-based model. The benefit of this approach is that it does not rely on manual observation or tracking device. We will only use image and bounding box to perform these detections. The research can serve as a fundamental step for future studies on automatic efficiency monitoring at the group level, paving the way for a more comprehensive solution in crew-based productivity tracking. Next, we move on to methods. Our framework is divided into several key steps. So first, we are using a CNN backbone with RNLI to do the feature extraction for each workers. Then, we build a fully connected graph where nodes represent workers and edge represent relationship based on the visual features. On the other hand, we use distance encoding and masking to refine the spatial relationships. And in last, we combine these two metrics to construct our relation matrix, and then we apply a cluster algorithm to detect groups. So the framework starts with a CNN backbone and RLI to extract the features for each individual. Then we construct a fully connected graph and update both graph nodes informations and edge weight with several rounds of message passing. On the other hand, we take the bounding box and apply spatial distance encoding and masking to represent the spatial affinity between each individuals. After that, we can establish a human relation matrix using spatial and visual affinities between workers. The spectral cluster algorithm is then applied to this matrix to identify groups based on these relationships. The algorithm effectively operates on constructed relation matrix R, unlike traditional k-means, which assume spherical clusters and requires predefining the number of clusters. Spectral cluster leverage the graph Laplacian eigenvectors to segment data based on intrinsic connectivity, making it more suitable for identifying worker groups in complex construction site scenarios. For model training, our loss function is designed to evaluate the accuracy of group detection by comparing the relation matrix to the ground truth affinity matrix. We test our framework on a dataset consisting of 13 real-world construction site videos, recorded under both sunny and cloudy conditions. The video focused on rebar installation tests, which involve workers frequently interacting and forming groups. The resolution of the video was Full HD, and they were downsampled to 1 frame per second for analysis. For the annotations, workers were grouped based on their interaction, or if they were worked on the same object. We use several metrics to evaluate our model's performance. First, we need to define what is a correct group detection. We use the matrix called health metric, which consider a true positive detection by computing the IOU of the predict and ground truth group compositions. After that, we can apply the standard detection metrics such as precision, recall, and F1 score to evaluate the performance. Besides the above metrics, we also conduct other extended metrics such as area under curve and MET IOU to measure the overlap and spatial consistency between predict and ground truth grouping. Now, we move on to the results. Our framework achieved an overall F1 score of 72.2% with 64.4 precision and 82.7 recall. As you can see in the visualization on the left-hand side, the composition of each group was correctly identified. Looking closely at the ground truth and prediction 2, you can observe that the framework successfully distinguishes different working groups, even when they are spatially close together. This demonstrates that the combination of visual feature and spatial information helps the framework learn the pattern efficiently. We also conduct an ablation study to evaluate how the framework performs with different weights of visual affinity and spatial affinity. As you can see in the table, when RD is weighted higher, the model tends to focus more on spatial information, which helps in situations where groups are close to each other. However, this sometimes leads to decrease in precision as the model may falsely group together workers who are not visually similar but are within a certain spatial proximity. On the other hand, increasing the weight of RE emphasizes visual similarity, improving precision but occasionally sacrifice recall when workers are far apart or occlude, as visual features alone might not capture their position accurately. In conclusion, we found that the model performs best when the weight of RD is slightly higher, as they lead to better spatial grouping without significantly compromising precision. However, here we highlight the incorrect predictions. The primary source of error in the upper right corner stems from intervening and occlusion of two groups, making it difficult for the model to differentiate between them. Additionally, since the current model takes a single image as input, understanding group dynamics and movement becomes particularly challenging. This limitation suggests that without temporal information, the model struggles to resolve ambiguities caused by overlapping worker interactions and visual obstructions. Conclusion: we have developed a graph-based deep learning framework for automate group detections. The system integrates both visual similarity and spatial proximity to cluster workers. It performs well on real-world data, achieving high F1 score and spatial consistency. However, limitations were observed in handling occlusions and overlapping groups, as well as difficulties in managing dynamic group memberships. Future work will explore incorporating temporal tracking and sequential modeling, such as RNN or transformer models. That's all for my presentation. Thank you for your attention.